Welcome back to Physics 141 Online. I'd like to do another example problem involving the conservation of angular momentum, showing how to use it to deal with a system where a rotating object in some sense changes. The distribution of its mass changes while it's rotating. So here is the problem. A boy with mass m/3 sits at the outer edge of a solid rotating disk with mass m and radius r. Their initial angular velocity is omega. So here's my picture of a rotating disk that has mass m and radius r, and then there's a boy, and I'll just draw a little dot here to represent the boy. The boy has mass m/3, and at the edge then is a distance r away from the center of the disk, which is the rotation axis. Okay? And the whole system then, we'll draw it rotating clockwise here with an initial omega. And then what happens is, we want to find the angular velocity of the system after the boy crawls to a position that is a distance r/2 away from the center of the disk. So imagine that he is able somehow to crawl in to a point not all the way to the center, but halfway to the center. So now the distance that the boy is away from the rotation axis is r/2. And clearly this is going to change the moment of inertia of the system. And so omega final is the quantity that we would like to find. We have our initial and our final picture, and clearly here we're in a situation where since the mass distribution changes, then the final velocity is going to change, and we'd like to apply conservation of angular momentum in order to analyze this situation. There's no net external torques, and so angular momentum should be the same before and after the collision, or before and after the boy moves. And clearly the rotation sense doesn't change, so the vector nature of the angular momentum is the same before and after. So I'm just going to write down the magnitudes of angular momentum before and after, and then set those equal to each other to solve for the unknown final velocity. So angular momentum for an object that's rotating about a fixed axis is just I times omega. But there's two objects here. There's the I of the disk, I disk omega, and then there's the I of the boy. And we could think of the boy plus disk as one single system, but I just want to make it clear that there are two parts to this, right? So I will factor out the original omega and write this as I disk plus I boy. And the final angular momentum will look quite similar, but the I of the boy will have changed. So what do we do? I disk, that's easy, because if this is a uniform solid disk, then the moment of inertia should be 1/2 the mass times the radius squared. Now what about the I of the boy? Remember that when we first defined the moment of inertia, we did it initially in terms of the summation, where we break down an object into all of its component pieces, and each piece has its mass multiplied by the square of the distance from the axis, which is what the r sub I means. So if the boy can be approximated as just a point mass, if he is small compared to the size of the rotating disk, then here what that tells us is the I of the boy, we can just take his mass m/3 and multiply by the distance that he is away from the axis squared. So that's his mass m/3 times r squared, because he's a distance r away from the rotation axis. And so that allows us to write down L initial as omega times the sum of these two terms, 1/2 mr squared plus 1/3 mr squared. And if we express those two over a common denominator, 1/2 is 3/6, 1/3 is 2/6, and so we get 5/6 omega mr squared. So that's L initial. L final, the only thing different about this will be the moment of inertia of the boy, because the spinning disk has not changed any of its mass, just the location of the boy. So I'll write this down very similar to what we had for L initial as omega final, right, times the moment of inertia of the disk, and that doesn't change. But in this case now, I'm going to put I boy prime. Just to remind me, this is different. This is not the same as the original one. And applying the same kind of reasoning here, I boy prime, the boy's mass is still m over 3, but now he's a distance r over 2 away from the rotation axis, and that gets squared, just like we had up here, m over 3 r squared for his initial location. Now the final location is contributes this distance r over 2. So we square that, and we're going to get 1/12 m r squared when we multiply that out. So L final is omega final times half m r squared plus 1/12 m r squared, and that's 6/12 plus 1/12, which is 7/12. So we get 7/12 omega final m r squared. And now we just set L initial equal to L final, and we solve for the unknown final angular velocity. Right? So this becomes, well, we got 5/6 omega. Ooh, sorry about that. That's not right. 5/6 omega times m r squared equals 7/12 omega final m r squared. And because both masses, the disk and the boy, are both related to this symbol m, the m's, we can divide both sides by m and they cancel out. We can divide both sides by r squared, and those terms cancel out. And so then all we have to do is solve for omega final, and to do that I'll multiply both sides by 12/7. So that gets rid of the 7/12. So we have 12/7 times 5/6 times the original omega, and 12 over 6 is 2, so we get 10/7 omega. That is the final angular velocity of this system. And let's just check it. Of course, units are fine because omega and omega final have the same units. They work out. As far as the magnitude goes, if we look at the problem, what's happening, of course, the boy is crawling in toward the center. And that means the moment of inertia that he has is decreasing. He's getting closer to the axis. And just looking at the conservation of angular momentum and thinking about examples that we're familiar with, like a figure skater, if we reduce the angular momentum of the system, then in order to compensate for that, the moment of angular velocity has to go up. And so the fact that omega final is greater than omega, that also makes sense. It doesn't tell us whether our factor of 10/7 is necessarily correct, but the fact that the angular velocity increased certainly agrees with what we would expect. So this problem highlights the way that we use the expression L equals I omega in order to find the angular momentum of a system that's got a fixed axis. And one further calculation we could do, although the problem doesn't ask it, would be to compare the initial and the final kinetic energies. And we'll have to see, if we did that, we would find out what allowed the system's energy to change. And of course, what's happening here, the boy has to do some work in order to crawl in toward the center. And as he crawls in towards the center, it makes sense that the kinetic energy of the system would change. So I'll leave that as an exercise for you to do if you're interested, and I hope this helps. I will see you in class.